Welcome, everyone, and thank you for joining this webinar on battery storage systems hosted by United Central Coast for Action, a program of the Slow Climate Coalition and Ecologistics. I am John Smigelski. I lead the United Central Coast for Action program. Just share my screen here. Taking off. Anyway, we deeply appreciate the support of our partner organizations, which help promote this webinar. We continue to work with our partners and with you and our audience to further our transition to a clean, affordable energy future and develop resilience in our communities. We're excited to bring you today's program on battery energy storage, law, safety, and technology with a trio of excellent presenters. Before we introduce them, some housekeeping. After the presentations, we'll have a Q&A sessions. During the presentations, please enter your questions into the Q&A feature. At the conclusion, we will direct those questions to one or more of the presenters. If we get several questions on the same topic, we will combine them so you may not hear your exact question. It's my pleasure to introduce Tracy Hunt, CEO and co-founder of Ecologistics, who will introduce our speakers.
Hi, and thank you, John, and hi, everyone, and thank you for joining us today. We're happy to be collaborating with the Slow Climate Coalition on Ecologistics' third and final in its critical conversation series for 2025. So I want to introduce our first speaker today, Elena Krieger, PhD. She is Senior Director of Research and Policy at Just Solutions, a national nonprofit focused on equitable energy and climate solutions. Previously, she served as Director of Research at an interdisciplinary energy science and policy research institute, where she explored strategies to integrate public health, equity, affordability, resilience, and other societal benefits into energy transitions. Thank you for being with us today, Elena.
Thanks for having me. All right, I'm gonna do my best to um, share my screen. So give me one sec and let me know if this comes up okay. Great. Can you see that?
Yes.
All right. So hi everyone. Thanks again for the introduction. I'm Elena. I am based out of Oakland, and I again run the research and policy team at a national nonprofit focused on equitable and just energy and climate solutions. And I also happen to do my PhD in engineering, working on batteries. So excited to be here and to talk to you. Um, I am going to, let's actually go back to the slide, talk a little bit today just about the landscape of energy storage in California, where we are and where we're going, why we need energy storage in the first place, what some of the benefits are, some of the risks, and sort of how we move forward to achieve those benefits while mitigating risks. And that will set us up to a deeper discussion from Richard and Kara that will deep dive into some of the sort of safety and policy solutions. So why energy storage? The most common application for energy storage we often hear is, well, the sun doesn't shine and the wind doesn't always blow, and so we need energy storage to make sure that we integrate renewables. And this is true. Energy storage can play an important role, making sure that we can meet our climate goals, bring renewables onto the grid, and displace fossil fuels, retire the gas plants that we've relied on for decades, and mitigate that climate and air pollution from those facilities. To see what this looks like, I took a snapshot of California's power supply earlier this year, this from August 27th. And this is the generation on California's grid at the utility scale throughout the day. And what we can see in this big green section here are renewables, which increase significantly when the sun is shining, as we expected. That's a huge swath of solar right there, and that's not even reflecting all of the solar on everybody's residential and commercial rooftops. And then we can see that demand goes up at the end of the day. And as the sun is setting and renewables are starting to disappear, we have this huge increase in that red chunk, which is the gas plants. So our gas plants are turning on in order to meet that demand at the end of the day. But what we're also starting to see is an increase in battery use. And so the purple section here are batteries, and they are charging. That's that little negative section that we're seeing sort of in the morning to the middle of the day, and they're discharging in the evening in order to reduce that need for gas plants to meet peak demand. So as we go forward and we bring on more solar and we bring on more wind, more batteries can also help us meet that later demand and address that intermittency and variability that we get from renewables if we want to reliably replace those gas plants. But this is not the only thing that storage can actually do on the grid. Our electric grid, very broadly, we often think about in three categories. We have generation, those are power plants and where electricity is coming from utility scale installations. We have transmission. These are high voltage lines that transmit that electricity from wherever it's being produced to individual neighborhoods. And then that's stepped down to the distribution level, and we have distribution wires that bring electricity to people's houses. And energy storage can play a really valuable role at basically every step of this process. So on the supply side, we can put storage with wind and solar, use that to integrate renewables. We can also use it to actively displace power plants. In particular, some of our most polluting power plants or most expensive ones and least efficient are called peaker power plants. They are often come on. They're not used that much, but when they are used, it's often on hot summer days that already have bad air quality, and they all turn on when we're all turning on our air conditioning to try to cool our houses. So energy storage can actively try to replace some of those. We can use energy storage instead of transmission. So instead of building new transmission or upgrading transmission, it can help reduce congestion. And transmission can take 10 years to build. It's hard to site. And energy storage can provide an alternative to that. And we can also use energy storage at the distribution level, both to displace need for upgrades into distribution wires, which is where we're seeing a huge amount of increase in costs on the grid. It's driving part of the affordability crisis. And we can use storage at people's houses to bring down bills, to comply with time of use or reduce demand charges at commercial facilities, and to increase resilience in the case of outages. And in many cases, we can do storage in a way that addresses multiple different buckets at once. One of the great examples I like to think of is that there was an oil-fired power plant in Jack London Square, just down the road from me, and it was impossible to replace, or very hard. We didn't want to replace it with a gas plant that would continue to pollute this dense, environmentally overburdened community. It's hard to site new transmission, and so the alternative plan presented was to put in a utility scale and distributed storage to get rid of this power plant that was burning jet oil in an environmentally overburdened community in West Oakland. So, in addition to grid benefits, and we sort of touched on this, energy storage can play a role for bringing about broader societal benefits. On the left side here, I put in a figure of California's gas plants. And we can see that they are in the plot. This is all the gas plants in relation to California's disadvantaged communities. These are places that have high cumulative environmental and public health burdens, and the gas plants are disproportionately located in those communities. We can target energy storage in a way that can try to displace the most polluting gas plants, the ones that might be in environmentally overburdened areas. And if we do it in a distributed way, some of that can also provide benefits to the communities who need it most. Bringing on renewables broadly has, again, climate and public health benefits. We can increase resilience at households. We can improve reliability with energy storage. We can, in many cases, improve affordability if we're choosing a least cost option compared to some expensive transmission or a peaker plant. resources and try to address some of those environmental justice and equity issues. Where are we in terms of energy storage? This is grid scale storage. There's actually all grid scale resources on California's grid over the last 5 years. That big blue chunk on the bottom is gas. We see yellow is growing, that's solar. And that turquoise chunk has taken off in the last few years. That's our utility scale storage. It is growing quickly. We also have storage at the commercial and residential scale. On the left side here, we can see all of the storage that is estimated to be on the grid from distributed and utility scale installations. How much do we need? Well, California modeling suggests that we actually need 3 times as much as we currently have on the grid. So what that means is we're going to have to more or less take the maximum amount of storage we ever put on the grid in 1 year and do that every year until 2045 if we want to meet our climate targets. There's some variations in this and different ways to do it, but it means that we need a rapid expansion of energy storage and renewables in order to try to electrify everything and do so in a way that's based on renewable energy. One fun fact I like to talk about is that we have nearly 4 gigawatts of pumped hydropower storage on the grid. So for many years, the most common type of energy storage that we used was literally pumping water up a hill, leaving it in a reservoir, and running it back through a turbine when we need energy. And we're still using that. That's hard to expand. There's environmental impacts from building out dams. It's dependent on having a mountain in the first place, but we're still relying on that as we're building out our grid. So where do we actually put storage? One of the main trade-offs is looking at whether these are large utility scale installations or distributed at homes and businesses. Utility scale sometimes is lower cost up front. Distributed can offer additional resilience and affordability benefits for the households who are adopting it. So there's benefits and trade-offs there. And can also often provide some of those distribution level benefits that you might not see at the utility scale. It can be easier to interconnect storage at existing interconnections. Let's say where there is an old gas plant can bring down costs and help meet local grid needs. And that gets me to what are called local reliability areas in California, or at least I think they were called that. They might have changed the term. These are basically regions where local resources are needed to meet that peak demand, the maximum amount of energy that is sometimes needed on those hot summer days or evenings, where there isn't enough transmission to really bring in electricity from other places. This is true in a lot of urban areas in Los Angeles and the Bay Area, where building transmission may take a really long time, and building out storage as well as renewables sort of at the local scale can help increase that reliability in that local region. And then again, we can sort of target storage and how we adopt it in a way that actively displaces some of our most polluting facilities as well. But there are drawbacks to storage. A lot of these are fundamentally related to the kinds of materials that are used in, particularly in different kinds of batteries. Upfront, mining causes all sorts of environmental and public health impacts. There are human rights issues with things like cobalt, which is often mined by children in Africa. What we need are increased health and safety mining standards and certifications to make sure that we're sustainably sourcing materials. Similar issues at end of life. We need sort of upfront funding and better planning for what we're going to do with all these batteries at end of life, and health and safety regulations and enforcement to make sure that materials do not pollute surrounding communities if they're being recycled or disposed of. One of the sort of worst examples of this is the Exide lead acid battery recycling facility, which is now a massive Superfund site that operated for 90 years in Vernon in the LA area. There's lead that's just almost impossible to get out from soil all throughout the community. Scientific researchers have found lead in children's baby teeth. They use that to try to track who is being exposed. This facility was violating a lot of the regulations regularly, and it just wasn't being enforced. Um, and so we need to make sure that as we're expanding all of the storage on the grid, that we are making sure that we're figuring out how to mitigate any potential similar impacts, even though we're not using lead acid battery, we're using other kinds of batteries at that end of life. And I'm not going to go too deep to this because Richard's going to talk about this a lot. We need to think about safety and during operation. One way to deal with that is with lower risk technologies. I'll talk about that a little bit, and then leave some of the discussion about how to train firefighters, work with communities, work on alert systems and things like that to Richard's conversation. So in order to think about some of the technologies, I wanted to talk really quickly about how a battery actually works. This is a lithium-ion battery. On one side, we have what is called a lithium metal oxide, and the other side is an anode made out of usually something like graphite. And there is some kind of electrolyte, usually liquid electrolyte, that can conduct lithium ions back and forth between those electrodes. And there's an electrochemical reaction that when the lithium ions go one way, there's a reaction that stores energy. And when that electrochemical reaction is reversed, it releases energy. And there's a circuit that is completed either through charging or discharging, where those electrons go through a load, or they're driven back into the battery in order to charge the battery, and the lithium ions again go back and forth during that charge and that discharge. What I want to draw your attention to here is this says model of a lithium ion battery, and it calls this a lithium metal oxide. There are a lot of different kinds of lithium metal oxides that can and are used in lithium ion batteries. So we often talk about lithium ion batteries just as one thing, but it turns out there's a whole ton of different kinds of lithium ion battery chemistries. I've listed some of them here. Lithium cobalt oxide and lithium manganese oxide are often what you get in consumer electronics. They tend to be dense, so people want them because they're portable. They tend to use more hazardous materials and are more prone to things like thermal runaway. Lithium nickel manganese cobalt oxide, I think, is the battery that was being used in the Moss Landing facility when it caught on fire, which I think Richard will talk about a little bit more and can confirm that. Nickel cobalt aluminum is what Tesla has been using more recently. Lithium titanate replaces the graphite electrode. And lithium iron phosphate is my favorite battery because I'm a battery nerd and really like batteries. But these batteries last for a really long time. They are less prone to thermal runaway. They can cycle thousands of times before they die, and they use a lot less hazardous materials. They're not quite as dense as other types of chemistries, and they were more expensive for a long time up front. But those prices have been dropping, and they are increasingly, thankfully, what we're seeing on the grid more frequently. And so that is starting to reduce some of the risk from utility scale installations of batteries. And again, Richard will talk about this a little bit more. There's a bunch of other stuff too. So we have pumped hydropower. We spoke about that briefly. You can compress air underground in a cavern and release that to run a turbine. Metal air bar batteries are an emerging technology. In particular, iron air is one potential option. It's less efficient, but it can discharge over a long time when you need long duration storage. Lead acid batteries are what we saw for a long time, but are a lot less efficient and don't last that long. So those are mostly being phased out. Flow batteries work on the same principle as the batteries we just saw, but a lot of the materials are actually liquids. Sodium sulfur batteries tend to be high temperature. You can actually store energy as just straight up hot and cold. You can make ice and use that for cooling. My grad school campus had a giant water tank. And when electricity was cheap, they would either make hot or cold water and use that for heating and cooling when electricity got expensive later in the day. Flywheels are actually spinning basically cylinders that can store energy. There's a whole bunch of things. The trade-offs between all of these are capital costs, operating costs, their density, safety, materials, and life cycle impacts, how long they last, energy security. Are we getting these in places that are, conflict zones? land use impacts, and then how quickly they can charge and discharge. And there's slightly different variations and trade-offs to all of these. And the right technology depends sometimes on what your specific application is. So what do we do moving forward to make sure that we continue to adopt storage on the grid and do so in a way that tries to achieve those benefits and mitigate impacts? A few things that I think we need: increased upfront community engagement around energy storage planning, discussion of things like community benefits agreements, safety, whether it should be distributed, whether people want it in the community, and make sure that process is done early and frequent and often, rather than after most of the facility has already been planned. Ethical battery sourcing standards and requirements, end-of-life funding, regulations and enforcement, ongoing research and pilot projects into safer materials and low-cost, long-duration storage. More on safety, which again, Richard will talk about in just a moment, and increased policies for gas transition planning, things like virtual power plants, which we can get to in discussion if we want, equitable access to storage and things like that. And with that, I'm going to pass it over to Richard to deep dive into some of the safety issues and how we can mitigate them.
Great.
Thank you, Elena. That's great. I'm going to introduce Richard very quickly. Our next speaker is Captain Richard Birt, who retired from the Las Vegas Fire and Rescue in 2021 after a distinguished 30-year career in fire service. A longtime advocate for renewable energy, Richard founded Solar and Fire Education, the acronym is SAFE, a program that provides free training to firefighters around the world. SAFE's mission is to teach firefighters and first responders how to safely mitigate structure fires involving photovoltaic systems and energy storage systems, while also demonstrating how renewable energy can help communities become more resilient to power outages caused by natural disasters. Thank you for being with us today, Richard.
Great. Thank you, Stacey. So let's jump into it. Let's jump right into it. I teach firefighters all over the world. I just got back from Spain from an incident that actually killed 2 firefighters. And the question is it safe in your neighborhood? Is it safe for communities? And so what I focus on is basically how it's going to affect the firefighters in their community. How does it affect the community? And what can the firefighters do strategies and tactics wise to mitigate an incident? So I was a firefighter in the United States for 30 years. I'm from England originally, but I was an early pioneer of solar, and I lived off solar and batteries, completely disconnected from the grid. And I understood what an amazing resource it was. Lived off the grid for 15 years. But also I realized what are the dangers to communities and firefighters if we start putting this everywhere. And we're at that point. You're going to have battery storage in your neighborhood. And the big question is, for the communities, for the fire service, for the civilians who have this battery storage in their neighborhood, is it safe? So a good example for you would be the Vistra power plant. So Moss Landing, what happened? What happened was, number one, the chemistry that was used in Moss Landing is called NMC. It's an older chemistry, and it's NMC. It's better than the long name lithium, nickel, manganese, cobalt oxide. But this NMC chemistry was an older chemistry, bit angry chemistry, and basically that plant should have been decommissioned, but it wasn't. There was an incident that happened, and what happened was basically there was a thermal runaway. The fire department are taught not to put water on it, but there was a sprinkler system that malfunctioned. There was a leak of water, and basically what you had was an incident where there was toxic smoke and there was water runoff. And it was a bad incident. It was a bad incident for the fire service, and it was a bad incident for the community with a very outdated, old-fashioned chemistry. But what's happening now is everyone's looking at that incident and going, no way do we want batteries in our communities. The thing is, the chemistry has changed, the strategies and tactics has changed, and the understanding of what's in your community has changed. So what we're looking at now is batteries, large batteries connected to the grid that are going to be of LFP chemistry, lithium iron phosphate. So I teach this to firefighters. What are the differences? There is a massive difference between LFP chemistry, which you're going to have in your neighborhood in large storage, and the NMC chemistry that is in the legacy plants that are being decommissioned, and the one in Vistra obviously burn up. So at this point, what do community people have to be aware of with lithium-ion batteries in their neighborhoods, in their homes? I task firefighters with filtering out the drama so we can actually solve the incident. Because if we listen to the drama and we listen to misinformation, what you're going to do is end up with bad strategies and tactics. And our job is to protect the communities. Our job is to protect firefighters' life safety. That is our main job. That's why we exist.
Richard, were you sharing your screen? Or did you have slides? It's we're supposed to be seeing slides.
No slides. I'm just
no
talking
slides.
for 20 minutes. Okay.
Got it.
All right. So at this point, I don't want to do slides right now because I really want to get to the point of what we're looking at is basically a very simple fundamental fact of a few safety mitigation things that the fire service can do that if the firefighters are happy with, the community should be happy with, because we're the people that deal with it when it goes wrong. So first of all, there are 3 chemistries. Get your pencils out, get your notebooks. This is being recorded. There's an NMC chemistry, there's an NCA chemistry, and there's an LFP chemistry. Pretty much that's what your world is made of. Right now, large storage has moved into the LFP chemistry. LFP chemistry is a very safe and stable chemistry. When it does catch on fire, or there is an incident where a battery goes into thermal runaway, you're producing a lot of hydrogen. Now, we learned early on with battery storage that you don't put that LFP chemistry in a confined building and put a roof on it and doors. What you do is you have independent storage units that are outside on a concrete pad. And if there is any off-gassing or burning, that hydrogen is lighter than air and dissipates. So what we've learned is, number one, to put storage outside on a concrete pad. And what we've learned also from, if it does catch on fire, the fire department does this. The fire department pulls up on scene, will look at a large storage unit burning, and they'll realize there is X number of kilograms of electrolyte and basically the components of the battery burning. And what we are teaching is not to put water on that. If we put water on the unit that's burning, we're just going to make the situation worse. So what we do fundamentally is if one unit burning and there's another unit next to it, because each one of these has storage in it, what we do is protect exposures, and we'll put water to cool down that unit, because we can kind of know when the battery cell is going to go into thermal runaway and kind of the temperatures. So what our job in the fire service is to let the one unit burn, cool down the other units, which we simply can do with water supply and spraying a water curtain on, which we do from multiple different scenarios. But the most important thing is let that one unit burn. Now, if we let it burn, what is it producing? It's producing mainly hydrogen. So if the hydrogen is contained, yes, we have an explosive risk. But if it's in the units that they're designing right now with blowout panels, basically it's just evaporating into the air. Now, the difference is what happened at Moss Landing. Yeah, that was an incident because, number one, the fire department was putting water on it, but water was being put on it from a sprinkler system. The water was contaminated. And the other part of this is the chemistry, NMC chemistry that was at the Vistra power plant had hydrofluoric acid in it. It had fluoride particulates in it, and it can create hydrogen fluoride. And there was particles of heavy metals. So you had nickel, aluminum, lithium, cobalt, and copper, and these particles were in the air. So you had this floating mass of very toxic gas, of very toxic smoke, and it was very reactive. It was a major problem in that area. Now they're working out what was contaminated, where did the water run off, and is there contamination in the water? These things they're studying now. The thing is, going forward, if you're putting large storage in your area, you are no longer dealing with that scenario. You're dealing with a very different chemistry. You're dealing with strong strategies and tactics where the fire department can pull up, let one burn, protect exposures. And now we're looking at a whole different ballgame. We're looking at the point where battery technology at the large storage level is one of the least concerns for you in the general public. I teach this around the world. If you talk to any New York firefighter, they will tell you the most dangerous thing is not the large storage in your community. The most dangerous thing is your e-bike or your scooter or your vape pen or your drill pack that you have sitting on your workbench, because there is so much of the bad chemistry. Like I said, NMC is coming into the United States, and we're doing a study on this. FDNY, the fire department in New York, is the largest fire department in the world, and we're doing a study on what are the risks across the board for lithium-ion battery and for solar to our communities. And the number one risk right now is what's in your home, not what large storage is, because we've changed the chemistry. We have solid strategies and tactics. I'm going to be teaching that whole area coming up. Again, we've got the strategies and tactics to deal with that. We know what's off-gassing. We know we leave it out in the open so the hydrogen basically dissipates. We know what's in the smoke cloud and how to mitigate that. So at this point, we're not looking at very, very high risk for the community. Where we're looking at high risk is basically where that e-bike is in your kid's room or in your garage, and it has a battery that doesn't have any ratings. So fire departments look at ratings too, because it adds or decreases the danger level. I'm going to task everybody at this webinar to look at their own home. After this webinar, it's recorded so you can play it back. Look for your battery packs in your home. From everything, you'll touch 25 to 30 lithium-ion batteries in your home. I want you to check this. I want you to check that battery pack has UL 1642. I want you to check it has UL 2054. These are ratings that the fire department will use to say, well, this is a lot safer than if you don't have these ratings. UL 1973. Remember these. Again, it's being recorded. 9540A, 9540B, UL 9540A and UL 9540B, and NFPA 855. Everybody didn't think they'd get homework from this webinar, but I teach firefighters, thousands of them all over the world, and this is how we're looking at this from a sensible point of view of what the chemistry is, what the danger to the community is. And at this point, we rate everything from the e-bike that burns up because it's charging in a brownstone in New York, and it's the only egress, and it produces toxic smoke. It doesn't have any of the ratings, and it's shipped into this country. All the battery storage, large battery storage you're going to see in your community has to meet all these regulations. Every one of these regulations have to be met for large battery storage. You mostly have 5 to 10 things in your home that have none of these ratings. So we start there and start working backwards. So at this point, it's really critical to understand that lithium-ion batteries are everywhere. It's a layer of technology that's come into our communities, into our homes, into our businesses, into our schools, and that we have to understand every aspect of it. And what the most important part is research. So the Fire Safety Research Institute, NFPA, does burn tests on all these different aspects that you're going to be touching in your lives. And what we're finding is large battery storage with LFP chemistry designed in a way that can't trap the hydrogen gas, can be designed in a way where the fire department can safely respond, safely set up water curtains and basically protection for the different batteries. So you only have one battery on fire, learning where that smoke goes, learning what is in the smoke and what is being dissipated, learning how to do shelter in place for the community. We're at a point where we're not seeing toxic runoff with that chemistry, and we are not seeing toxic plumes of smoke that have particulates of heavy metals, what we're seeing is a fire event that burns out over a couple of hours, that we have to be aggressive with protecting exposures and basically look which way the smoke's going. And most of these batteries, the important part to remember is most of these batteries are connected to some sort of transmission because that's their job. So we're looking at them being put in areas where they're not in a primary school parking lot. And that's the other balance to this, is understanding, where do you put batteries in a community? Where can we safely put a battery? And understanding the chemistry, understanding the plume of smoke, understanding whether we can get water to protect exposures. All these things the fire department are working hard on. The question that the fire department is pushing back to the communities is, what's in your garage? What's on your charger? Do you leave your charger on? Or do you take the battery off as soon as it's charged? A simple thing like a timer on your lithium-ion battery can make the difference between a battery being unstable. So the fire department is actually taking this information that we need to keep communities safe and going from the large storage to the EV vehicle to your e-bike or scooter, and looking across the board what we're seeing. And communities have to understand what we see, because we only get called when it goes bad. We aren't the cheerleaders of anything. What we are the people who have to solve a problem when it happens. And so our mitigation and our focus is on firefighter safety, on life safety, incident stabilization, and property conservation. All those things under the lithium-ion batteries right now are saying large storage has come a long way. It's a lot safer for the community. What we're looking at now, fundamentally, the higher the risk, the smaller the unit, is what we're seeing, with any of the standards applied. So to me, the biggest concern for the fire service is water supply for large storage. If you put large storages, where are you going to get the water to protect the exposures so all the battery units don't catch on fire? Number two, the training, so firefighters understand when they pull up and see a large burning battery, that our job is not to basically do what our instincts say, is put the wet stuff on the red stuff, put the water on the fire. What we're working out is be comfortable with that burning, acknowledge it's burning, acknowledge the gases. We have 5 gas meters. We are looking at the environment, and right now with LFP, we are not seeing anything that is telling us this is critical. And what we're doing is monitoring that air so we can do shelter in place if we need to, just like we do for other things. One of the amazing things we're doing is the research on a working house fire has more toxins in it, in the smoke, than a lithium-ion battery. A lot of the times we are seeing similar toxicity, except for a few separate things in electric vehicles. So when you see a house fire, when you see a building fire, the smoke is just as toxic as a lithium-ion battery. There is no change. If anything, LFP has more hydrogen in it, so it's less toxic. So at this point, it's understanding it from a grassroots point. It's understanding it from an emergency responders level. And I would say what happened in Moss Landing was worst case scenario. That should have been decommissioned. That was an old chemistry. It did produce toxic smoke with particulates of fluoride in it, with particulates of heavy metals. It was a disaster. There is no doubt. Looking at the LFP that is put in now, it is completely different. And we've got to understand that moving forward and start really looking at Moss Landing. Is that in your home? That's the biggest thing. I tell firefighters all over the world, is that chemistry from that Moss Landing, that Vistra power plant, in your home? And I can tell you it is in your home. And there is must be 20 to 30 different contacts of that kind of chemistry in your home. Not large storage that's being put in California now. That's LFP. Completely different chemistry. So you got some homework. Informed decisions on renewable energy is critical for everybody, not just for firefighters. Thank you.
Thank you, Richard. Okay, our last speaker is no stranger to many of you. Kara Woodruff is a 30-year plus resident of San Luis Obispo and a business graduate of Cal Poly San Luis Obispo. She is an attorney, financial planner, and mom, and received a joint JD/MA degree in law and public policy from Duke University. As a former project director for national conservation organizations, Kara negotiated and raised funds for the conservation of over 100,000 acres in SLO County, including at Hearst Ranch, Cambria Pines, Irish Hills, and the Carrizo Plain. She is a member of the Diablo Canyon Decommissioning Engagement Panel and a senior policy advisor for Senator John Laird, 17th Senate District of California. Welcome, Kara.
Thank you, Stacy, and hi, everyone. I know a lot of you out there, so nice to have you here today. As Stacy mentioned, I am the district director for Senator John Laird, and I'm here on his behalf this morning to talk about some of the legislation that he has authored to improve battery safety. Backing up a little bit, Senator Laird represents the 17th Senate District, and that includes all of Santa Cruz, all of Monterey, and all of San Benito counties, plus most of San Luis Obispo County. And that's about 1 million people along the Central Coast. And if you ever have questions about battery storage or other issues, I just wanted to provide my email address so that you can get back to me at your convenience. It's just kara.woodruff@sen.ca.gov. So I'm going to talk a little bit about Senator Laird's legislation, but I wanted to back up just a little bit and talk about the context for the need to improve battery storage safety. Right now in the state of California, we have 17 gigawatts of battery storage already online. And that represents, as Elena mentioned, utility, residential, and commercial battery storage facilities. But 17 gigawatts is a lot. By comparison, the power generated by the Diablo Canyon power plant is 2.2 gigawatts. So battery storage is quite a big percentage of the total generation of the state of California. It's also grown at an incredibly quick pace, which is why we're all running to try to keep up to the technology. It has increased by 2,100% since 2019, and we're only about a third of the way towards the total battery storage goals that we hope to reach by 2045. Interestingly enough, the cost of battery storage has gone down extensively. In fact, since 2010, the cost of building, running battery storage is down 93%. So it's considered one of the cheapest renewable energy sources available. Batteries have also become increasingly important as we respond to climate change events over the last many years and increasing days of hot weather where people are running their AC and doing other things to keep cool or keep warm during the winters. We used to have, the latest one was in 22, a flex alert, so that when our use of energy was dangerously approaching the amount that's being generated in the state would send out flex alerts. And many of you probably remember getting a text on your phone from the state of California urging you to turn down your AC or otherwise reduce your energy usage. But because of batteries in large part, we haven't had a flex alert sent out for 3 years now. And a big part of that reason is because of the prevalence and growth of battery storage facilities. Having said all that, we have some issues, and I think Elena did a great job of describing the risks associated with battery storage. And even before the Moss Landing fire in January of this year at the Vistra facility, there were other incidents across the globe, across the state, including even in Senate District 17 at the PG&E Tesla facility in Monterey, as well as the Vistra facility. There were other incidents where they had problems that created the loss of different storage packs even prior to the catastrophic fire in January of 2025. So in response to these events that have legitimately caused pretty grave concern for our constituents and the prevalence of battery storage, Senator Laird has crafted, authored, and ultimately had signed by the governor and passed into law 2 pieces of legislation. The first was SB 38 that was enacted in 2023, and it did a number of things, but the heart of it was it required every operator of battery storage facilities to prepare an emergency response and action plan, and that they had to coordinate with local emergency response agencies in preparing that plan, and then it had to be submitted to agencies and the county where the facilities are located, so that in the event of an emergency, people had information ahead of time about how to respond to that emergency. And then after the January 2025 disastrous catastrophic fire in Moss Landing, Senator Laird authored SB 283, which is called the Clean Energy Safety Act. And again, it was also passed and signed into law this year. It was in response to the Moss Landing fire at Vistra, but intended to provide a safer path to battery storage in general. It was endorsed by and supported by the California Professional Fighters Association, in addition to the International Brotherhood of Electrical Workers, who were very concerned about their own team members, making sure that working around battery storage was safe for members of IBEW. So the legislation is somewhat complex, but there's 4 primary components. The first is that if you are intending to build a new battery storage facility and you submit an application, ahead of time you have to engage and confer with your local fire authorities on the design of the system, mitigating the risks, and creating detailed emergency action plans. The second element is that after a facility is constructed, but before it goes online, it has to be inspected and signed off by the local fire authority. And the cost of that is borne by the applicant, not by the county or a local government. Third, the law required the Office of the State Fire Marshal to create regulations and rules to upgrade the safety requirements of all new facilities. And it would also further describe the types of facilities that would be allowed under the new law. And one of those requirements is that none of the new buildings can be combustible, which was the case in Moss Landing. And ultimately, these new regulations have to adhere to the National Fire Protection Association's 855 standard, which assures the highest level of battery storage safety. And then finally, an important component of SB 843 is that it expressly allowed local jurisdictions to adopt more stringent standards to meet the needs that might apply to their local communities. This again passed by the state legislature and was signed by the governor, and it is now law. And Senator Laird continues to look to the new legislative session to consider other areas that need to be looked to. I think we learned a lot today about the chemistry of batteries. It can be very important, more on the structures and maybe even locations. So those will probably be explored in the next legislative session. I think I'm going to stop there in the interest of time so that we have plenty of time for questions and answers. So thank you.
All right. Thank you very much, Kara. And thank you again to all our speakers for taking the time to be with us today and share your knowledge. We're now going to address as many questions as we have time for. Let's see. John, did you see the questions? Do you want to read them?
I do. Yeah. So
Okay.
here's the first one. This is for Elena. Are there any efforts you're aware of to reuse rather than recycle batteries that have reduced capacity?
Yeah, that's a great point. I think, first of all, ideally, we would reuse as many batteries as possible before putting them through any kind of recycling and materials recovery process. It's been a bit slow. There have been a couple pilot projects. I know that the Sacramento Municipal Utility District, for example, was reusing some old electric vehicle batteries old batteries for its electrical vehicle chargers. More recently, there's a company called Redwood Energy that started as a giant battery recycling facility, and they have actually found that they're starting to get more traction in the battery reuse space, and have started a couple of projects that are actually larger scale. And there's a handful of others. So yes, they are starting to move forward on reuse, but it has not scaled as quickly, I think, as many of us probably would have hoped. And as some of these batteries reach end of life, again, the adoption of electric vehicles and utility scale storage is taking off. And in another, 10 to 20 years, we're going to start to see a lot more. I hope that that will continue to increase.
Okay. One more question for Elena before we move to Richard. The question is, what about solid state batteries? Are they an upcoming technology? How do they compare density, reliability, cost?
Yeah.
Um,
Yeah. So solid state batteries, when we looked at that diagram of a lithium ion battery and we looked at those two electrodes, and there's a liquid electrolyte typically that goes in between them that helps the lithium ions transfer back and forth. Solid state batteries have a solid electrolyte instead of a liquid electrolyte. Um, they tend to be safer. They often are more energy dense. You can charge them, or at least that's the goal, faster, and discharge them faster, which is great for electric vehicles. And they're always a couple of years out in terms of when they're going to be commercially viable. I think, I don't know, I'm not deep in the weeds on solid state batteries. There are a couple of announcements, particularly out of China, of a few companies that are saying that they're going to have commercial lines starting in 2027 or so. That's really exciting. They might actually be commercially viable. Right now, I suspect that the first few are going to be pretty expensive, like we saw with lithium iron phosphate batteries and others, and there's going to be some kind of economy of scale before they begin to take off, and be more commercially viable, particularly at the utility scale. Again, that sort of density and fast charging component is very valuable for electric vehicles and somewhat less important when you're looking at different kinds of trade-offs, at the utility scale, although the enhanced safety, again, would be a huge value.
Okay. This one's primarily for Richard. So Moss Landing battery energy storage system came online in 2020, and the community was told it was safe and the latest technology. How quickly is tech evolving, and will these current batteries also be obsolete in 5 years?
Yeah, so that's a great question. If you look at anything, especially connected to electrical technology, your computer, your phone, how many times have you changed your phone out from 20 to 2025? What are we looking at? It's the same thing with this technology. We're looking at a vast, growing, huge amount of change. And the good thing about the change, I would say to people, is the change is getting safer. And I would say we start out with some really angry chemistry because that's what they had. And we've got safer and safer. And like with the solid state, we're at that point. One of the biggest things, too, with the changes in technologies, LFP, yeah, is going to be out of date. But is it safe and relevant now? There's equipment that we use in the fire service that we change out when the technology gets better. But there's equipment in the fire service that's been around for 100+ years, and it's one of them's water. And guess what? It's still the best thing ever. So sometimes new doesn't mean better. What we look at is safety. Is safety safety? And what is the level of the safety of that technology at this day? And in 5 years from now, there may be a new technology, but is it the safest technology? It may not be. But there will be changes, and there will be changes in chemistry. And one of the biggest weak points, and this is where the changes, is that separator between the anode and cathode. That separate, pull one of your hairs out. It's as thin as a piece of your hair, and it's a piece of plastic. And it lets the electrolyte do its job and the ions move. The trouble is, we found that little piece of plastic is very, very vulnerable to damage. Now, one of the things we're studying with large storage is it sits on a concrete pad and it's not doing anything but charging and discharging slowly. And it's pretty gentle. The system's pretty gentle. Whereas the EV car, you drive it down a road, you hit the curb twice, you get rear-ended, you get side. what happens to that separator in that cell, deep in that battery? And so we're starting to understand things they never ever think about with storage. And what we start understanding is stationary large storage with the chemistry and with how it's built right now is kind of safe because it's a mellow, chilled out environment, whereas the car is getting knocked around and banged around and heat swings. So it's really interesting to see it from a safe point of view. But you're going to get change, but sometimes what we're going to look at is the change might not make it safer.
So kind of follow-up question, how do you assess the safety of newer types of residential batteries for solar systems that do not contain cobalt?
Okay, so what we do in the fire service is we burn them. We put them under stress, and we put them under every kind of stress you can imagine, and we burn it. We've been doing that for years. We've been burning houses, we've been burning buildings, we've been burning everything and seeing what does it do? When does it catch on fire? Your couch. We have looked at your couch every which way you could imagine to see what would catch it on fire and what would be bad. And so we do that with lithium ion. And that's how we're learning. We're learning the differences in chemistry. We're learning to understand what those mean. So, like I said, the LFP chemistry right now is the gold standard because we understand what it off gases and when it burns, but we also understand the hydrogen. So it's followed on from that. And what we've got to the point is understand how much hydrogen it off gases, how explosive it is. So we're not putting it in buildings anymore. We're putting it on a concrete slab so it can just dissipate. So that's how we do this. There is millions of dollars spent on burning to see where the weak points are and see where we can improve it.
Are there other battery storage facilities similar to Moss Landing that are in need of decommissioning?
I would say I teach PG&E safety team on lithium. I just taught 200 of their safety team, and I tell PG&E every time I teach them, look and see what chemistry you have in your plant. Very, very simple. Look and see what chemistry you have in your power plants. And I would say if they're older chemistry, it's a good time to look at that and go, were they vulnerable? Is that angry chemistry? How long have they been charged and discharged? And at this point, I would say there are. And it's up to the industry to actually look at that and say, is it a risk benefit right now to change that older chemistry out, knowing the facts we know about that chemistry and about charge and discharge cycles? So yes, there are. And as a community, know what chemistry is in your neighborhood, know what chemistry is in your house.
Okay. And this is a question for either Richard or Elena or both. How can we place batteries strategically to reduce the risk of fires, and are batteries a poor option for certain communities given these risks?
Where do we place the battery? Is that what you're saying? What was the question?
The idea is reducing the risk of firefighters by using batteries to reduce transmission.
I think it's wildfires. The question is wildfires.
Wildfires, yes.
Okay.
Sorry,
so wildfires. Yes. So
yes.
One thing that PG&E is very, very interested in is this. Wildfires are caused a lot of the time by transmission. So you're moving a large amount of electricity over this skinny little line, and you've got to make sure that line is up and running. And sometimes there's only one feed into a community, which makes it vulnerable for power safety shutoffs, but it also makes it vulnerable for wind events. PG&E looks at it the opposite way. They go, you know what? If we don't have to run hundreds of miles of high voltage wire through a really, really dry area, and we could put a battery plant right next to where we need the demand, oh my word, are we looking at improving fire safety? So that's one way of looking at that, is basically storage in geographic areas that make sense, where they can actually not have to transmit so much high voltage over a very, very high risk area, is a very, very good thing.
I think another option to think about here is that if we look at distributed energy storage, there are options to also build out resilience. So if we can think about distributed batteries, both at critical facilities, at resilience hubs, and particularly at homes, the people who may be most vulnerable to outages, the elderly, people with medical equipment that relies on electricity, that even if the grid does go out, those batteries can provide backup power for people who need it most. And ideally, you can aggregate those all together and meet grid needs like deferring those transmission investments that Richard was just talking about. And so there's an opportunity to sometimes use distributed battery storage to provide that resilience and maybe reduce the need for some of that using those transmission lines at times of high risk.
Yeah, I would completely agree with residential batteries. One of my classes for the fire service is obviously on residential battery and solar panels. And to me, it's a huge advantage for a community to start introducing solar and batteries. One of my proudest things as a firefighter is after Hurricane Maria, we put 19 solar and battery systems on stations across Puerto Rico. 19 systems that are independent. And they're saving lives today because the Puerto Rico grid is so bad and they have so many power shutoffs. So in California, the idea of having residential solar and storage, EVs, and then having large batteries, what you're doing with California is basically building a grid out that the big players like PG&E are happy with too, because they can't meet the power demands. So what if you have 1,000 homes in a community that don't have a power safety shutoff? They don't need the power. But what if they've 1,000 homes have got batteries, full batteries at 4 o'clock in the afternoon? Well, PG&E are going, oh my God, we need some power desperately. Where are we going to get it from? Guess what? They can get it from a localized battery that can, in 0.3 milliseconds, put onto the grid, and now you've stabilized the grid and you don't have a brownout and you're not stressing. The other part of this people don't understand. Power draw stresses the units. If you can keep that power draw by using your solar and batteries at home, by using large storage, what you're doing is you're putting less stress on that grid. That's very, very congested. And so it's a win-win for everything. I think what we're seeing is a reduction in wildfire if we can strategically put microgrids in where they're on homes and then there's a large storage, maybe feeding them one way in and one way out. There's so many areas in California, especially your coastal areas, where there's one feed coming in. And if that feed goes down, how many of those vulnerable people in that neighborhood are on oxygen? In your area alone, how many people are on a nasal cannula? It's 2 liters per minute. I was a paramedic for 27 years. That basically keep that person alive. If the power goes out, they have an oxygen bottle. Yeah, it'll last an hour. What if the power outage is for a day because of a wildfire or 48 hours? Now we're looking at if somebody has a residential solar and batteries, that's the difference between emergency service being activated, which they can't respond to anyway because they're fighting a fire. So it's all connected. It's all connected. And it's a very interesting way of looking at the electron and how we use it.
So some questions for Kara. Has Low County or any other county in California been involved in proactively identifying suitable locations for battery energy storage system sites in relation to residential or other sensitive areas?
No, I think counties throughout the state are always thinking about what types of uses of land are appropriate for what areas. I mean, the simple way they address that is zoning. If you have a site that's zoned industrial, the whole point of the zoning is to invite those activities that might be well suited for a particular part of the county and not suited elsewhere. I don't know of any specific effort where they've said battery storage can go A, B, or C, but not elsewhere. But generally, zoning takes into account where you're going to allow industrial uses. But following up an earlier question, the location of where you put battery storage can be very, very important. So recently, I took a tour with some of the people on this call out to the Darden facility that's just being constructed now in Fresno County. It's really fascinating. It is in the middle of the Central Valley. They are building a facility on top of former ag lands, but the ag land, the soil is no longer viable for ag. There's not adequate water. And so it's fallow land that is pretty far away from where anybody lives or works. And it's a place where you don't have trees and other wildfire hazards. It's not a forested region. And they're building a 2.2 gigawatt site that will be constructed within a year. Half of that is solar, half of that is battery. And it's welcomed by the local communities because it's a source of income, it's a source of jobs, but it doesn't create some of the problems that facilities that might be located right next to heavily populated areas have seen in future years. And having community support is really, really important. As I'm sure most of you know, Vistra not only operates the Moss Landing facility in Monterey County, but they have a proposed facility in Morro Bay. But there was very significant local opposition to that. And they also had some issues with the Coastal Commission in citing it there. In fact, in 2024, the Coastal Commission wrote a letter to Vistra noting some of the problems they might have in obtaining permits. And eventually, Vistra decided to abandon their plans. They decided to not go through the county to the city of Morro Bay to proceed with their battery storage site. They opted to not proceed an alternative route through the California Energy Commission. And so now there are no plans to build in Morro Bay. Some people think that's a good outcome. Some people think it's a lost opportunity. But I do think it's really clear that if you do intend to operate a facility, you probably need to have your local community on board, because if you don't, you might run into problems actually getting your facility constructed. But I'm sure there are some communities that welcome the benefits that battery storage can bring, and it can be very advantageous from a tax revenue perspective, from jobs, et cetera. So an applicant for a new facility would be well advised to work with the local community, be very transparent, and seek to get their support. Otherwise, you might have a situation where you start up with a great plan, but it doesn't go anywhere and you don't have any opportunities after that.
Thank you. So we talked about behind the meter storage for consumers, giving them a larger cost benefit and some resiliency of their own. What's the best storage safety you should apply at your home? What you should be looking at?
Great. That's a great question, because that's what I do a lot of teaching on the residential, obviously, side of things all over the world. So the good thing about the United States, which is massive, is our rapid shutdown. We have rapid shutdown code. And in Europe, where I teach all the time, they have zero rapid shutdown. So if things go south on a roof, they have a DC arc of 4,000 volts, 4,000 degrees Celsius, and it doesn't turn off if the sun's shining. Whereas in the States, we have very, very strict rapid shutdown. So number one, America is the leader on safety for residential batteries and storage. There is no doubt we are setting the path. Number two, the safest way to go is to look at the architecture. With solar and batteries, it's really interesting. There's high voltage DC architecture where the solar makes very, very high voltage. Up to 600 volts can go on your home. DC, direct current, 600 volts. When you plug in your toaster, it's 240 AC alternate current, which is a very, very safe electricity. The reason they went with alternate current has a break in the system, whereas direct current is just full on and there is no break in that system. So what I tell people is look at your architecture, what you put in your home. Number one, it's got to be LFP, which it is for residential. Number two, it meets all those standards I talked about. But number three, do you put it in the house or outside the house? Now, California, great place to put batteries outside, but put them in the garage. Again, there's rules to that and codes. But one of the biggest things I would say is look at your architecture of the electricity. Now, there's things called microinverters, which what they do is they go under each panel. So this little unit goes under each one of the panels. And what it does is it changes direct current from a panel, let's say 60 volts direct current. And it goes into this microinverter. And what it does is this microinverter changes that electricity direct current into 240 AC, which is in your home. And what it is, it's just a safer electricity, because we've dealt with 240 AC for 100 years in a fire service. And usually if there's a fire with AC in a home, it's because someone's plugged in 20 things on a strip, right? So I would look at the codes. I would look at where you put the battery. And I would also look at the architecture. I would go with a microinverter architecture because it's alternate current from the panel to the battery. So these are very, very simple things that when you're talking to an installer, you can ask, do I have a microinverter? What kind of chemistry and where are you planning to put the battery?
A personal story on that. I bought an EV recently and I was ready to plug it into my garage outlet. My next door neighbor said, you don't want to do that. You have a really old home. You need to hire an electrician. So I did. And the electrician came out and said, it's a good thing you called me. If you just plugged it into the wall, you would have had potentially a catastrophic situation. And so they had to rewire my garage and part of my house really to make it a safe situation. And now I charge with ease. But had I not gone through that step, I could have had a big problem. So my recommendation is if you are going to buy an EV and charge it at home, make sure you call an electrician and make sure you've got a good system to back you up.
That's a very good point, because the EV is a whole separate thing in itself, because we're finding the EV, number one, the chemistry is an LFP. It is NCA, and they're changing it to LFP slowly, but EV vehicles have to have angry chemistry in it because you've got to charge it quickly and discharge it quickly. And what we're finding is that separator in those cells are vulnerable to crashes and so on and so forth, and they take a lot of electricity. So again, the biggest thing, if you decide to put renewable energy in your home, don't do it yourself. What you want to do is you want to look at, don't build the battery yourself, because that's what we train firefighters on, the people that decide to build batteries themselves, and it ends up being a disaster. So go with companies, reputable, bigger companies. Look and see, number one, is it DC or AC? Is there a microinverter? And again, what is your amperage on your home? You may have a small, older home that has a 100 amp service. You may have to upgrade that to a 200 amp service. And again, these are the pros. This is what they do, and they evaluate all that, because you're adding a whole layer of electricity to your home. This isn't, we're just going to put some solar panels up and a battery. No, what you're doing is adding a complete layer of technology to your home, and then you're parking a layer of technology either in your garage or on your driveway.
And we had a question, how does a runaway happen? So just that, is that the barrier breaking down? Thermal runaway.
So there's two things that are very dangerous to firefighters. And even before the thermal runaway is when basically shit hits the fan. I hate to say that, but this is when fire happens. There's a lot of heat and it burns. Before thermal runaway, these cells can get damaged, and what can happen is it can off-gas it, and it off-gases is a very white, low-temperature gas, because these basically off-gassing can happen at 300 degrees Fahrenheit, and that white puffy gas is, number one, full of hydrogen, and it's very, very explosive. So what we worry about is that cell structure. You've got that battery, and it goes into a module, and all those modules make up one battery. So you have a cell, a module, and a battery. Each one of those cells is in charge of that little unit of the anode and the cathode and the separator, and it's doing its thing. Now, if one of those interrupts and starts getting basically damaged, what can happen is these cells and this energy, they can create their own heat. So in the fire service, we look for what created the heat. Was it a match? Was it some gasoline? What created this fire? With these batteries in your home, they can create their own heat. They can create their own oxygen. They can create their own chemical reaction. So thermal runaway is the damage to that cell. And then from there, you start having instability, and then you start having shorting, and that's what creates the heat. That's what creates the gases, and it just goes to the next cell and the next cell and the next cell. So thermal runaway is when everything starts taking off, everything starts burning, and it starts producing a chemical reaction that the fire department has a very, very hard job interrupting. So we usually let it burn.
Okay.
Just to add
Well, I want to,
quickly,
okay, ahead.
basically what happens is when you have that battery and it's charging and discharging, there's a primary electrochemical reaction that's supposed to happen. When your lithium ion is going into one electrode and then back into the other, there is one reaction that's supposed to be driving the voltage output and the electricity output that you get. But there are also side reactions that can take place. And those side reactions tend to increase when there's high temperatures, and they tend to increase when there's damage to batteries. And that battery damage can happen just from cycling. The lithium ion going in and out of those electrodes actually causes mechanical stress and little microfractures over time and just increases the chance of side reactions. Some of those don't go anywhere, and then some of those can feed on themselves, as Richard was talking about, and lead to runaway chemical reactions that are not the basic reaction that the battery is based on. And that is what is driving the production of gases that they're not supposed to be producing and other things like that that can then catch on fire, produce waste heat, and drive more side reactions.
Okay. Well, thank you. Well, we went past time, and I just want to thank our presenters for just an excellent, informative webinar. And reminder, all registrants will receive a copy of the webinar recording, and you can find previous webinars at the slowclimatecoalition.org website. And feel free to let us know any topics you'd like us to cover in future webinars. And really, thank you for participation, and thank you, Stacy, for co-hosting. It's great to put this together with you. And thank you very much.
Great. Thank you, everybody.
Yeah.
Thank you.
I thank you.